So we're going to build out chair structures. Originally, when you first assemble your chair, it's probably not going to be actually in a chair conformation right away. What's going to probably happen is that the bonds are going to be kind of at different angles. You're going to want to pull them into that chair conformation. So right now, we've just made a six-membered ring by using the six carbons and just kind of connecting them. So we have six tetrahedral pieces. We connect them all together. We're going to get something like this. It's not a chair yet. What we do want to do is start to pull this into a chair conformation. So we're going to take the every other carbon. I'm just going to pull one of those bonds down, and we want to pull them kind of towards each other at the bottom of the ring. For your proper chair structure, you want it to actually touch in three different points. So you should be able to set this down on a table, and it should be able to stand there by itself and not fall over. And we want these positions to all be kind of alternating carbons and able to kind of sit down on a table, so they're all going straight down. We can also see the tops are all alternating straight up, and so those straight down positions and the straight up positions, these are the axial positions. And so those are the bonds. They alternate up and down on each carbon, as we can see, or as you can see when you build it out. And those are going to be our axial positions. And it's important to know that they do alternate on each of those carbons, because we are going to have to be drawing in where groups are going to end up on the ring. And so we're going to have to know, are we going to draw this group straight up, or are we going to draw it straight down, or is it going to have to be out to the side, things like that. And so for this one, we have our chair structure. How we normally look at our three-membered rings is we kind of look at it like this. So we can kind of see that hexagon shape that we are maybe a little bit familiar with at this point. That's how we normally draw them. That's how we draw the hexagon on the page. That would be a six-membered ring in 2 dimensions. For 3 dimensions, and to figure out where the groups are in space, we are actually taking it from this representation and looking at it on its side. And so we're actually going to be looking at it in this representation here. Specifically, when we look at it on its side, we can't just look kind of at any angle. The angle you have to look at is actually with this upside down V in the front. So these two bonds have to come up to the middle. This would not be the right way of looking at it, for example, because these two bonds go back down in the front. So you're going to want those two bonds to go up towards that carbon there. And that's what we're always going to be looking for in our chair structures. And then we kind of have our side bonds to the ring, and then the two that go up to the front, and then they go down to the back. And so that's kind of how we draw out that chair. Again, we're looking at this on its side. When it comes to a question and we want to put a group on this ring, if we're looking at the question that we saw in the notes with the bromine, it was going out of the page. And so we're just going to take a little colored ball to represent where that bromine is, and to figure out where to put it on this chair, we can actually go back to that original structure we had. So the actual question was first drawn out with this hexagon, and then we had a bold line over here. We had a bold line coming off of that carbon with the bromine on the end. And so what we're going to do is we're going to put our bromine on this carbon, and we see that we have 2 choices. We have this one that's coming out towards you, or we have this one that's actually going away from you and towards me. Because it was bold, that means it's coming out towards you, and so you do have to add your little ball to the one that's coming out. So we're going to put it on the one that's coming out. And then now that's how it was in our example. This that bromine is coming out towards you. What we're going to do to draw our first chair, just to get a chair structure drawn, we're going to do a rotation like this. And that's kind of where we can see that that bromine is on that carbon at the very back, because this is the front carbon that we have. So for our numbering in the notes, we had this as number 1, then 2, 3, 4, 5, and 6. So this is got that carbon kind of in the back right of that chair structure, and that's why it's there, just because of how we decided to rotate it here. So this is going completely up. What we do, so it's axial. What we do want to do with this one is we want to go through that chair flip. And so we're looking at the chair, how we would draw it on our page. Then drew it on our page. And then what you want to do for your chair flips is you want to take the ring and grab two opposite sides. So I'm grabbing the one with the bromine, and I'm grabbing the carbon directly across the ring from it. So we kind of position ourselves like this. For our boat structure, we're going to go and bring the one up. So I'm holding this one the same, but I brought the one on the right up. So we can see that this is our boat structure, and you can kind of see that it looks a little bit like a boat, more so than the chair. It looks like a chair at least. And this is our high energy structure. So the chairs are lower energy. This is our high energy. It's kind of like the staggered and eclipse. This is like the eclipsed version. It's higher in energy. This is not a conformation that the molecule is going to spend a lot of time in, but it does have to go through this to get to the other chair conformation. And so this is high energy. Why is it so high energy? That's because this group is actually going to be interacting with this group over here. So they're actually really close as they're going to get in this ring. So we brought them together pretty close. That's very high energy. So what we're going to do now is we're going to continue this, and we're going to, so we brought this one up, we're going to bring this one down. And then if you really kind of have to force it, because sometimes it'll kind of be stuck out there. So if you aren't sure, just kind of bring those three together at the bottom again, just to make the nice chair structure. And then originally when we did that, if we kept that bromine on the same carbon, we would actually see that that's at the back of the molecule still, but we're not looking at the chair properly, because this is the two bonds at the front are going down to make a V. And so that's why we actually have to do that rotation so that we can look at that chair properly again. So we're looking at that upside down V at the front of the molecule, and that's what you need to do. And that's kind of why it looked like that bromine maybe hopped to this carbon here. That's not the case. We just had to do the rotation after we did the flip so that we were looking at the chair structure correctly. And so that's how we're going to do the chair structure itself. We saw also what happened with that bromine is it went from being in that axial position. So in our other chair, it was basically at this position, and then now it's in an equatorial position because it's going straight out and the axial is going down now. So this is going to, we didn't break any bonds or anything. We just did that rotation or that flip because the chair can't actually rotate, it's too rigid. So that's why we do that flip. And then we got that bromine going equatorial. So one more time to kind of show that chair flip, if we wanted to flip it maybe back, if we maybe built it out in this conformation, we're going to grab opposite sides of that ring. We're going to bring one side up. This makes the boat structure. I'm going to bring the other side down, and we're going to kind of fix it so it looks more like a chair. And then we do have to rotate it to get that upside down V. We could have also rotated it like this and then just drew the group at the top. So at the front carbon, really doesn't matter as long as you have that upside down V. When you're doing your chair flip, you didn't break any bonds, you were just doing it the way that we showed. That's going to be important. So in the chair flip, we basically have anything that was axial in the original chair conformation, that's going to turn into being equatorial, and vice versa. Anything that was equatorial in the first conformation is going to be axial in the second. So because when we did our flip, our first chair, if we're looking at it properly, our first chair looked like this. And then once we flipped it, so we had axial and then we went to equatorial and did that rotation. This is actually going to be more stable chair conformation because our big group is equatorial. And so that's going to be more stable because when it was in its axial position, we were able to interact with the other hydrogens here. That's that 1,3 interaction at the top of the ring. So or flagpole interactions it's sometimes called. So big groups, we always want them to be equatorial because they're actually closer to other groups if they're axial. And so you're always looking for which chair conformation has either the group equatorial. In this case, there was only one group, so we want that to be equatorial. That's going to be the more stable chair. Or you want the biggest group or the most groups to be equatorial. So sometimes you'll have a big group and a small group. The big group being equatorial is more important than the small group being equatorial. If it kind of flips in the chair structure. Also, if you have many groups, if the more of the groups are equatorial than axial, that's also going to be more stable as well.